Hey guys, welcome back to this second analysis video for motion and falling marbles. So essentially all that we've been looking at in these analysis videos is not walking you through the 16-page version of the lab, but really what we're just trying to do is make sure that you're able to do primarily three of the graphs. So in video one, we looked at the graph as velocity final versus time, and we were able to solve that out and derive the equation. The velocity final is equal to velocity initial. Oh, not equal, that's crazy. But plus acceleration times time. So we were able to kind of derive that out of the first one. And if my recollection is smooth, our acceleration was 9.8 meters per second square, which is kind of so good that it almost shows that the data wasn't actually, fake, but it is kind of interesting to see how good it came out to with a little error in there. So anyway, to this video, we're going to take a look at this graph, a position versus time graph of the data. So what's cool is if you've already typed your data into Google, it becomes real easy to create another graph. So I'm going to go over here and I'm going to click and let's go insert graph. And this time, so insert chart. And of course it tells me I don't have any data. So let's go over here. I want a scatter plot again. And for my data, this time I'm wanting a position graph. So position. So there's my position. Thank you, sir. Position versus, and for my x-axis, I want, click on select data range, I want time. And so that's how easy it is to make our graph. And as you start looking at this graph, some things should kind of stand out. Let's see, chart, for the title of the chart, let's see, this is position versus time. And then let's see, we need to do our axes as well. Our horizontal axis is time in seconds. Our vertical axis, our y-axis is position in meters. Notice how I always put my units in there. But still, this graph looks not very straight. So let's go put a trend line on it. So click series, go down, and let's just click it, add trend line. And when we add that trend line to the graph, it's pretty clear that this is not a linear curve. Matter of fact, it looks like we've definitely got a curve in here. So now, essentially at this point, this is where it becomes known that we need to linearize this graph. So let's take a look at it then. Whoa, that was kind of crazy. So we tried this graph, and this is what we ended up with. We ended up with a parabola. So now the question to you is, how do we linearize this graph? In other words, how do we take position versus time, and the goal is to try and turn that into a straight line graph. So what can we do to this data? Well, it's easy. You've seen this curve in math class before. No telling how many times you've looked at this. And what is that the equation for in math class? It's the equation for a parabola. So if you want to linearize this, all we have to do is essentially think about what a parabola is. The equation for a parabola is y equals x squared. So to linearize this, what we need to do is go in and change the t to a square. Now, so what's actually really easy to do, and that's why we're doing this in like Google. So let's just go up here and add another column. And I don't want to delete these graphs, but I would definitely like them kind of moved out of my way. Let's go add another column up here. So let's call this time square, because you can also do trial and error. If there's another lab you may have already done, let's see, seconds square would be have to use the little caret for my unit. So there is that. And now what I want to do is square my time. So go over, find my time, and then caret square equals, and now it's as easy as I can go through here and boom. All right, so now let's go back and let's add another graph. And so we're going to end up with a page full of graphs before this is said and done. So this time, insert chart. And once again, I've got to go up here. I want to get this graph a little out of the way. And let's go up here. I want a I wish it would just by default pick that by now. But I want a scatter plot, and I want position for my y-axis. And now for my x-axis, I want times square. Good job. Times square. And now when we look at this data, oh my goodness, look at what we got. Except for the fact that apparently it's not going to let me drag it. We have got what appears to be a straight line. Let's just go ahead and look and see if it is a straight line. Add trend line, and sure enough, look at it. It fits all the way across. So let's go in and customize this graph a little bit. Let's change our titles on here, chart title. So this is position versus time square. And what we've been doing is we've been establishing the relationship for an accelerating object. Let's see, that would be seconds square. We've been establishing the relationship for position and time for an accelerating object. And what we've been able to learn is that it is a square relationship. Finish typing that. Boom. Oh, that's beautiful. The only thing we've still not done is a chart title, and I thought we did that. I guess not. So this is position versus time square. And you're going to have a lot of graphs to turn in. That's what's really neat about doing this in your Google Sheets. You can kind of take them and clean these up. I need to do one more thing though. So let's go up here, click, and let's edit my chart. Let's go back to customize and go to that series. We've added the trend line, but now let's get an equation. So here is my equation, and I'm going to see if I can't copy that. Come on, guy. Give me that equation. There we go. So I'm going to copy my equation, and let's move it over to this page where we're done. So let's do a four-step analysis on this position versus time square graph now. So to do the four steps, step number one, we made it into a straight line. So we established the relationship between position and time, and we figured out that it's a square relationship. If you were unsure, you could have modified one of your two variables and just tried to see if it made it straight or not. Well, ours came out straight, so we're relieved, and that gives us y equals mx plus b is our equation for line. Step number two, replace y with, I'll just leave it with p for position equals, you could have done d for distance or y for, you had a choice of variables. M times, in place of x, I'm going to write t squared plus b. Step three is replace your slope with your actual value. So in my case, 4.91. And don't forget the unit. So let's go up here. Rise over run. Meter divided by, wait a second. That was the unit we got from the last one we did. So a meter per second square, t square, minus, for me, since I've got that negative, 2.16 times 10 to the negative 3, which, once again, I'm going to make that a 0 because it is such a small value. So now it boils down to, you need to try and identify, what does this even mean? Well, I will take you for a flashback. Remember, the slope of the last graph was 9.8, and now the slope of this graph is 4.9. Notice that it's the same unit, which means that this position is equal to, and you'd probably be prone to go ahead and just write, aha, meter per second square. So that's an acceleration, and you're not wrong. That is an acceleration. But the thing is, we've already established the acceleration of the object in the first graph was 9.8. So compare 4.9 to 9.8, and you'll see that that's actually 1/2 of the acceleration. So one of the equations we use in physics, I'm going to write D. One of the equations we use quite often, and I wrote V sub O. It's hard to break habit. One of the equations you'll find in like your textbook is this one, 1/2 AT squared. They'll say that distance, some textbooks will write this like this. They'll say change in X, which is displacement, which for all practical purposes, you're right, it's still distance. But what we have done, oh, some textbooks will even write y, and some will even just say y. You've got so many equations you can use, but they're all the exact same thing. It's just different notation in physics. So the thing is, you've derived the 1/2 at squared. So you should be looking at, though, how come we didn't have this little VIT portion in there? Why is that absent from the equation we derived? Well, just remember, it's not absent. It was right here, but if you remember, what was our velocity initial? It was 0, which is why our intercept came out to 0. So anyway, that's graph number 2. So there is a third graph you will ask to be doing linearized in the graph, and that's to make a velocity final versus, I'm just going to go ahead and write D for distance. You could have wrote P for position. Again, it's all semantics. It does not matter, especially to me. I'm not grading your work. Sorry for that joke. Anyway, let's take a look at this. So the great thing about, doing this in Google is it makes it super fast and easy. We're ending up with more graphs than we know where to put them. Your screen is, well, I just drug a title on that one. Your screen, however, is going to be bigger than mine, so you should be able to move these graphs around so you could turn them into your teacher a whole lot easier than I can. But now let's do something. Let's go up and let's do one more graph. Insert. So here we go. Chart. You should know where we're going. Fast forward through this stuff if you know exactly what you're doing. For data, though, I want to do a graph of final velocity versus, for my x-axis, I want to do distance or position. So there's my position. Okay. Horizontal. And when I look at that graph, let's go and do the trend line thing again. Let's customize. And I'm going to label it as always. And again, feel free to fast forward. Final velocity versus position. And I'll be a little lazy. You should know that for you need to put in your horizontal and vertical. But let's just do something. Series. Look at the trend line on that. And so what we notice is that this is not a linear graph. So we've kind of got the same problem that we did a second ago. We've got a graph, but it's not a linear graph. So let's kind of take a look at something. So you're going to have to think pretty good for a second. If you look at that curve, it actually looks something like that. So now the last graph we did, it actually curved up, and that fit that y is equal to x squared in terms of equations. So now look at this curve. It's just the exact opposite. So how could you straighten out this data? Well, hopefully you've already quit this video because you're like, aha, Mr. Cole, I got it. I know exactly how to linearize this graph. How can you turn that curve? In other words, in what way can you manipulate these variables to straighten out this graph? Well, if this one was y is x squared, in this case, it's the exact opposite. So we should square velocity final versus distance. And if you're watching this video going, Mr. Cole, you're giving everything away, meters square, second square. Well, you're not supposed to be watching this video unless you're just plain stuck anyway, is the idea behind it. So let's go back to Google Chrome and let's see if we can't actually make one more graph up here in Chrome. So we need another column. Velocity. It's harder to... If you're wondering why I type kind of slow, my keyboard is detached from this monitor, so it kind of, that I write on, so it kind of makes it a little difficult. So that would be, I'm just going to write meter per second, and then I'm going to put my caret, because I want to show that my units are squared in here. So this is why the great thing about doing this in Chrome is, though. So go find my velocity final, and then all I've got to do is square that column. And so now I can take that and just drag it right down. So now I've got my list of squared final velocities. So I want to make a graph of velocity final square versus position. So let's come down here and let's go back. You should, again, hopefully you're not watching this video. You got it. You're good to go. So scatter plot, but I'm going to finish it because that's just kind of how my brain is wired. So I want a graph of, boom, velocity final square. Okay, I want that for my y-axis. Now for my x-axis, I want to have position. Okay. And lo and behold, when I look at that graph, it's turned out to be beautiful at this point. So when we look at it, go back, change your title to, in this case, velocity final square versus, I'm going to write distance. You could have also wrote position on here. And now let's go down here to series. Let's add our trend line to this. And whoa, what a beautiful looking line. And now let's also, if you know by this point, label it. So user equation. Make sure on yours that you add your vertical and your horizontal as well in there. So I'm going to go back because what I really wanted was this. I really wanted that equation. So I'll go copy. And now let's kind of pull this over and take a look for a second. So we've linearized this graph by doing this square, and it came out with a straight line. And let's go back. Let's add our equation. And now let's do the four-step analysis on this. And we've kind of, at that point, we'll have looked at the major components of this lab. So let's see if we can't break this down a little bit. So let's get into it. I'm feeling like I'm going to go with black ink just because. Feeling something different. It's always red, red, red. So step number one, y is equal to mx plus b. Step number two, replace y and x with your variables. So for me, it's velocity final square equals m times distance plus b. You could have also used p for position. Let's give myself a little bit more room. And for step three, substitute in velocity final square equals your slope and units. Do not forget the units. And so what in the world are the units going to be for this one? Well, let's look. You had velocity square for an x-axis. So that's meters square, second squared, rise over run, divided by meters. Wait a minute. When I divide by meters, that actually, because that's like dividing by, multiplying by 1 over m. Wait a minute. I've got meters per second square again. What is this? Some kind of a nightmare? Meters per second square times d plus b. Oh, what did I forget to do? I forgot to put in my value for b. Good grief. Sorry, somebody's knocking at my door. It made me forget certain things. So in my case, it's negative, but you should know that the negatives obviously does not matter. And the unit would be, oh, what would be the unit for that? Let's see, it would be a meter square second square. Sorry, my screen got scrunched. Hey, say that 5 times fast. And then step number 4, what in the world does all this mean? Well, first off, you already know that that's going to be my 0. So that's out. You've seen this meters per second square. You should recognize that as an acceleration. So you know that velocity final square is equal to acceleration times distance. But wait, the acceleration of this object we already know is 9.8. So that means in this equation, my answer is actually coming out to 2 times the value. So wait a minute. So have I seen this equation before? Well, yeah, I've seen this equation before at this point. So I know that velocity final square is equal to, you'll see this in your textbook, velocity initial square plus 2 times AD. Wait a minute, but ours doesn't have this velocity initial in there. Ours doesn't have this. Why not? It's 0. So what we've done in this lab, and we've done a lot more, but if you just did your 3 basic graphs, you've established the 3 most common equations we use when solving kinematic problems. And so that is exactly what we've got. This was what we got from our second graph, and then from this third graph, we've established this. So when you look in the textbook next time, you're going to know exactly where these equations, I'm going to write delta x because that's the way I'll probably look in your book, but delta x and d essentially the same thing for most of what we're doing. So anyway, hope this helps you out, and good luck in all your other problems. Bye. Bye.